Alright, here is question number 3. And we're asked basically to do two different things here. We're asked to look at this figure, and it's sort of a part of a rather famous geometry problem of a figure like this, where one right triangle is built upon another right triangle, and then on another one, and on another one, and so on. And we're asked here to find side lengths, 4 different side lengths, and 3 different angles. Okay, so for us to do that, we have to consider what tools we need to use. And, you know, maybe you even need to, if you need to in your mind, separate out the right triangles. You've got this one here, where that's 3 and 4, and this is A. So you got to find the hypotenuse of the right triangle. If you can't see these relationships without doing that, then go ahead and do that. Just make a little sketch of each of the triangles in there, and then add information to it as you figure things out. Alright, so this is an A, not a 9. Alright, and we're going to find this length right here. And how do you do that? Well, the easiest way would probably be to use Pythagorean theorem here. We have the 2 legs of the right triangle. They're 3 and 4. So 3 squared plus 4 squared equals A squared. 3 squared is 9, 4 squared is 16. 25 equals A squared. Square root 25, and we happen to be able to get an exact integer value, which is 5. So A equals 5. Alright? And now, looking at the next right triangle, this length that we just found, 5, is not only the hypotenuse of the first one, it is the leg, one of the legs of the second right triangle. So, again, if you need to draw that off to the side, do it. Because otherwise you might get confused. Now, if you can see it in there, and I think most of you can't, but if it's really a problem, then draw it off to the side so you can see what values we got here. We're trying to find B now, and that's this length here, which is the hypotenuse of this right triangle, but also the leg of the next right triangle. So we're going to see a pattern emerging here as to how we solve these. So we use the answer we got for the last question as part of our solution to the next one. So 3 squared plus 5 squared equals B squared. 9 plus 25 is B squared, and so that's 34 equals B squared. Now we've been asked to find exact values here. So when we square root 34, we're not going to go to our calculator and find out what the square root of 34 is, because that's not an exact value. All that's going to tell us is what a decimal approximation of the square root of 34 would be. This is the only way to express the square root of 34 as an exact value. That is the square root of 34. And so that is the length that we have for B. So we found the first 2. And now, as you can see, we've got another right triangle built on that. And so this is the square root of 34. And then we've got 3 for this side. So we know the 2 legs. It's the square root of 34 and 3. Now we're going to find C. So, again, Pythagorean theorem. 3 squared plus the square root of 34 squared equals C squared. And you're going to see why, as you get into higher math, why these types of values are so much more useful if we leave them this way, if we don't get decimal approximations for them. Because when I take the square root of 34 and square it, what do I get? I get 34. So I get an integer value very easily here. 9 plus 34 is C squared. So the square root of 43 equals C squared. Alright, so there we have that. Square root of 43 equals C squared, so we're going to square root of C squared is C, and the square root of 43 is the square root of 43. So we have found this length right here, which we call C. Alright? And now we're going to find the last one. Let me get a clean slide for that. We found all these lengths. Now we are dealing with this triangle right here. We know that this is 5. That's one of the legs, and the other one is the square root of 43. So square root of 43 squared plus 5 squared equals d squared. Square root of 43 is 43. I'm sorry, the square root of 43 squared is 43. And 5 squared is 25. So 43 plus 25 is 68. 68 equals d squared. And then we have the square root of 68. So d equals the square root of 68. There are our 4 exact side lengths. 5, square root of 34, square root of 43, square root of 68. We used the Pythagorean theorem to find all of them. Alright. Now we're asked to find some angle measures. So let's take a look at that. We're asked to find x, y, and z. And we happen to have all 3 side lengths for all of these triangles that are that these angles are in. And so as a result, we could use inverse SOHCAHTOA functions, these ratios, either with tangent or sine or cosine. And I'm choosing to use tangent here. Here is angle x, the length of the leg that crossed from it, the opposite leg is 4. The adjacent leg here is 3. So second tan, 4 divided by 3 equals 53 degrees. So there we found angle x, 53 degrees. Now we're going to go find angle y. Okay, its opposite leg is the square root, there's 5, that is, right here, 5. And its adjacent leg is 3. So I'm going to use the tangent again. I wouldn't have to, I could use either of the other two. But it's convenient to use the tangent. I'm kind of establishing a pattern here, so I might as well use it. And I would get the same value no matter which of them I used. 5 divided by 3, so tan, negative 1. 5 divided by 3, and that equals 59 degrees. Alright, now we have one left to find up here, angle z. And the 2 legs are the square root of 43 and 5. So we can do that one now. The opposite leg is the square root of 43, the adjacent leg is 5. So here we have our tangent ratio. Remember, we're trying to find angle measures when you see this. When you're using that second function, we know side lengths, and we're using them to find angle measures. We use the regular tangent, sine, cosine. We know an angle measure and one side length, and we're trying to find another side length. So that's how you decide which to use. There are your 3 angles that you were asked to find. Alright, so this is question number 3. See you on the next one.